Okay, in our last lesson we defined Kirchhoff's point rule and loop rules, and we did a quick example using those definitions, but we didn't really need Kirchhoff's laws. In this one we do, because you look at it and this isn't just a matter of saying, okay, here's a series resistor and this resistor is in parallel with this. Because we got this battery here, it changes the circumstances. Things are indeterminate. Just by looking at it, you don't know for sure what's going to happen quite readily. All right, so we just can't make this into an Ohm's law problem. So if you don't believe me, go ahead and try and see if the results give you correct answers. Well, you'd have to set the circuit up to see that. But you will not get the same answer as we will using Kirchhoff's rules, which we really do need for this circuit. So I'm going to define this current as I1. Going through the 4 ohm resistor, I'm going to call that I2, and a separate current, namely I3, through this other resistor. 3 different currents here. You could say that, if you want, that this is total current coming out of the 10-volt battery. That's fine. But in any case, splits again. We don't even know, because of the orientation of this battery, if this current is in the right direction. Again, it doesn't matter. What we're doing is establishing what we assume to be true. If we're wrong, the results will reveal it quite easily. But the thing is this. We have how many unknowns? That's right, there's 3. We have 3 currents. We don't know what any of them are. I1, I2, I3. So to solve for those currents, we need 3 equations. 3 equations, 3 unknowns. That's why this gets a little tricky, especially with even more complex circuits. However, you can often use the point rule to reduce the number of unknowns down to 2. And so we're actually going to do that. So here's a point. We know that the currents in is currents out. Therefore, I'm going to choose this idea that I3, well, if it wasn't for I2, it would be, I3 would be I1. I1 coming in, I2 going out. But it's I1 minus I2 then would be I3, right? So I1 minus I2. Now we need 2 equations. Yay! Because we've just used we have an equation here, namely an equation for I3. So when we see I3, we can replace it with I1 minus I2. All right. I am going to choose loop number 1. I'm calling loop number 1 this one here. I'm going to analyze it clockwise. Notice I have other loops. I have this whole outer loop, and I have another loop here. So there's 3 possible loops. We got loop 2 here, and we could have this whole outer thing, call it loop 3. We only need 2 of these, 2 of the 3. There's lots of data here now, more data than we need. Because we've used the point rule to get us to only have 2 unknowns, namely I1 and I2. It's the only thing that we really don't know, because once we know those, we'll know I3. So getting 2 equations is good enough. I'm going to use loop 1. And let's go ahead and analyze it. So first of all, starting here, I have a rise of 10, and then minus 2I1, because it's a drop across the 2. And then we continue to progress through I2, and it's minus 4I2. And we're back to our starting point, so that's 0. And I'm going to use loop number 2. Loop number 2, where do we want to start? I'm going to start at this point. I'm going to navigate across the battery, plus to minus. It's a drop, so it's minus 5. And then it's minus 5I3. And I'm going to come back up here. Now, this is a little tricky. We're going to go in the opposite direction of the current. The voltage is higher on the top side than the bottom side. So if we're going from the bottom to the top in our analysis, we're rising in voltage, going from bottom to top. So it's plus 4I2 equals 0. So that's how you write the 2 equations. All right, so we have our two equations, and we solve those, and we're done. That's all there is to it. Now, I'm going to, basically, what we would like to do is make one of the coefficients the same as in both equations so that one of the variables drops out. So I'm going to divide loop 1 by 2, that equation. We get 5. Actually, I mean, this lends itself to just dividing by 2. And all I'm doing right now is I'm going to divide this by 2 in order to make it simpler. So 5 minus I1 minus 4I2 equals 0. And then that's equation 1. And equation 2, minus 5 times I3. I3 is I1 minus I2. Notice what I did. Plus 4I2 equals 0. So that's equation 2. I was premature in what I said about making one of the coefficients equal. It's true. We're going to do that, but we're just not quite ready yet. All right. So I'm going to rewrite this equation 2 here still. You know, I got this together. I'm going to break this out. Minus 5I1 plus 5I2 plus 4I2 equals 0. So there's equation 2. Notice that we can still simplify this. We're going to bring this together. 9I2. All right, so equation 1. Notice I'm rewriting these things a lot to keep them together. And we're just about ready to do something with them. Equation 2 now, minus 5 minus 5I1 plus 9I2 equals 0. And it's at this point that I want to do something with one of the equations so that when I add these together, one of these variables goes away. And then our work is essentially done. So I'm going to multiply the top one by 5. Why? Because I want the I1s to go away here. That's what I'm going to make happen. So actually I'm going to multiply it by negative 5 because they're already both negative. We need to make one positive so it cancels the other one. So here we go. Minus 25 plus 5I1 plus 10I2 equals 0. Just multiplied the whole thing by minus 5. I'm going to leave equation 2 alone, so let's rewrite it. There you go. Now when we add these together, as you'll see, minus 25 and minus 5, minus 30, plus 5I1, minus 5I1 goes away, and then we just have this, 19I2 equals 0. Now there we only have one unknown, so we can solve for I2. I2 is 30 over 19, which is 1.58 amps. Now once we find the first variable, the first unknown, we just solve for I2. We now know what this current is. Yay. Because we can take this value and sub it back into one of the equations. What I'm going to do is sub it into equation number 2. Doesn't matter. You could stick that into here. It doesn't really matter. And then I1 will pop right out. And then I3 will pop right out of that. So I'm going to do that on the next slide. So here we go. Minus 5 minus 5I1 plus 9. Sticking in the 1.58. That's I2 equals 0. So we get 5I1. Bringing that over to the other side equals 9 times 1.58 minus 5. All right. So I1 is equal to basically 9 times 1.58 over 5 minus 5 over 5. 5 over 5 is 1. Giving us I1. There we go. And then the last part, I3, which is I1 minus I2. There are the numbers. And there's the answer. And we have solved for the unknowns in that circuit. You would not get the same results trying to do it with Ohm's law. Go ahead and try, and I think you will be convinced.